Good morning, everybody. Welcome to the session with CII and JOVIX. We're going to be discussing today some trends that we've been seeing in the industry and regarding around aerospace, automotive, and also electronics as it relates to the supply chain. With me today, I've got Dr. Edward Anderson from University of Texas, and I also have Dr. Bill O'Brien from the University of Texas as well. And so what we're going to go through is the first part of this presentation is going to be a discussion about the current trends, as I mentioned, as it relates to supply chain of those three areas. And then we're going to follow up and dig in a little bit deeper as how some of these trends and some of the research that's been done can overflow into construction and take a look at that with a live Q&A that'll be moderated by Dr. Bill O'Brien and questions fielded by Dr. Edward Anderson and myself. So looking forward to the session. With that, I'm going to kick it over to Dr. Edward Anderson and let him run through his part. Take it away.
Thank you, John. Again, my name is Edward Anderson. I'm a professor at the University of Texas McCombs School, and I teach operations management, and I also teach information systems. I am going to be talking about trends and best practices that have been uncovered by research in adjacent industries. And as was stated earlier, I'm going to concentrate primarily on the automotive industry and aerospace. I'll also talk a little bit about the electronic industry because it might be a harbinger of things to come with respect to these other supply chains. Now, a couple of things I need to talk about up front as background. First of all, a lot of my colleagues in construction say to me often, well, what can we learn about industries that produce widgets? And that's a reasonable criticism. They're right. Really, the better parallel is to look at new product development. So new product development in the automotive industry, which is the creation of new cars, that's a 3-year-long process. It costs about $3 billion. If you want to throw in a new engine, that's going to cost you another $3 billion. So these are comparable to big projects in the construction industry. In aerospace, the last major jet that was designed was the 787 from the ground up, and that was about $32 billion. So that gives you a flavor of what we're talking about here. A couple of other differences. Owners, or their equivalents, which are usually referred to as original equipment manufacturers or OEMs, in the manufacturing industries are not only the operators, but they make money, which is pretty obvious in some sense, off of sales of their products. But the suppliers also make all their money off the sales of those products. So they don't get paid for the product development project per se. So that's a wrinkle that has to be brought up. The other one is that the OEMs actually maintain a lot of engineering in-house. In particular, they hold on to the systems engineering or integration piece, which is if you take all the various components that are outsourced to 100-odd suppliers, somehow those have to be spec'd up front so that they're coordinated. And then, much like the King's Men and Humpty Dumpty, those all have to be brought together again so you get a coherent product that matches the original concept. The other thing is that in the automotive industry in particular, they own some of their key technologies in the sense that they engineer them. There is no major automotive company, for example, that does not make its own engines, or it does not make its own bodies. And the reason for that is because of that integration piece, the engines and the bodies just touch everything else. So they found it more effective to hold them in-house. Last thing, the industries I'm talking about, suppliers are not used as particularly as they are in construction. Vendors and suppliers are synonyms. And they also include what we would call contractors. There is a lot of data on these adjacent industries. I've been researching with my colleagues these industries and a number of others as well for about 25 years since I was a graduate student at MIT. In addition to that, there is a wealth of research that has been done by prior authors such as Leiker, James Womack. By the way, James Womack and his group at MIT actually coined the term lean manufacturing. What's sometimes forgotten is they also coined the term lean project management and lean product design. Lastly, as part of CII, I've actually been going back again with my colleagues and trying to update the latest trends that we've seen in the past couple of years. We've actually been talking to people directly in about 10 different firms in these adjacent industries. So the main findings that we've been seeing is there are widespread use of strategic partnerships, widespread decomposition of systems engineering integration. So I was talking about how do you break up the component or sub-project functionality and then eventually bring it together. And what's happened is that used to all be done at the OEM level, say a Ford or a Toyota, and now it's being pushed down to their suppliers, such as their electronic suppliers, such as in the automotive industry, their seat suppliers, chassis suppliers, and so on. Aerospace has done this as well. There's modularity and standards. Those exist in great number and are becoming more prevalent, if anything. And of course, there's the move towards digitalization. So now I'm going to talk about each one of these in turn in a bit more depth. The strategic partnerships concept is that there are a small number of long-term core suppliers that work with OEMs. And it's an interesting relationship. So there is an ongoing exchange of innovation roadmaps by both the suppliers with the OEMs. And those meetings occur on a regular basis. These aren't related to any particular project per se. So they're not even at the programmatic level, they're at the firm level. Now, based on those, when a project is actually started, there is collaborative planning with the suppliers early in the initiation phase, and sometimes actually prior to concept select. Who are these partners? There are a couple of criteria at a high level. One is, how critical is the subsystem to the functioning overall of the product? So for example, we know that in the automotive industry, your entertainment system is a big part of the consumer experience. However, which entertainment system you put into the vehicle is pretty independent of the rest of the functionality of the vehicle. And hence it's not a critical partner in the sense of impacting all the other components that make up the product. Whereas electronic controls are exactly the reverse. The other criterion is that once you figure out which types of suppliers are important to you, you also look at the individual supplier itself. What are their metrics? What are the behavior? And so on. One concept that's really important is that there are both formal and informal contracts. The formal contract is what I mentioned earlier. Rewards are based on piece part profits from the assembly of the final product, not for execution of the product. And of course, there are other components to that as well. For example, you have to be able to meet any demand that is forecast by the OEM, for example, 2 weeks ahead of time. On the informal side, there are a lot of patterns behavior that are expected, and you really can't put them into a contract. And these, if they are going to work, have to be ingrained in the company's cultures, processes, and executive management on both sides. The thing is, these take a lot of time to develop. We all know cultural change takes quite a while. Process change, a little bit quicker, but again, it takes some time. The one thing that can change really rapidly, at least as far as been seen in history, is executive management support. So, for example, in the 1990s, General Motors had gone to a great deal of trouble to move from a relationship where they essentially exploited their suppliers and moved to a partnership. So they had strategic suppliers, and they would even do that with all their suppliers up and down, no matter how much of criticality that they would have and how much of an influence on the product that their parts would have. Now, interesting enough, there was a gentleman named Ignacio Lopez who was brought in as a vice president of procurement, and he immediately moved to, okay, who has the lowest price? And oh yes, you better be decreasing your piece cost suppliers 5% year over year. And oh yes, if you can get another price that isn't as good as your competitors, we'll take your drawings and move it over to the suppliers, the other suppliers. And the other suppliers, of course, can give a lower bid because they didn't do the original development, and they don't have to advertise or amortize that. Needless to say, this turned into a mess. The suppliers ended up gaming and hiding things, and basically, I wouldn't call it cheating or anything, but they treated General Motors as an adversary, and this proved to be problematic. And about 5 years later, actually less than that, Lopez was thrown out. The only problem is that General Motors, because their trust with their suppliers had been destroyed, it takes a long time to reaccumulate that. A last point. I talk a lot about trust here, and it does exist, but this isn't Pollyannish. So, for example, Toyota, which is considered by many to be the best of the automotive industry in terms of managing their suppliers, in their purchasing area, they have a group of really top-notch engineers who are experts in the fields of the various components that they're purchasing, and they spend a lot of time reverse engineering those to figure out what the cost should be. And if they get some partners who are a bit abusive of their relationship, then Toyota will pull back or punish them in some way. For example, one of their key suppliers of electronic systems was Denso, still is Denso, but Toyota began removing volume for it because Denso was getting a little too, in some sense, independent and not treating Toyota as its prime customer. Another finding, and I know this is controversial, so I have to be careful about this, are tiers. And tiers is in some ways an unfortunate name. It implies a power relationship. Now, to be fair, there is indeed a power relationship. The OEMs know they have power in the automotive and aerospace industries. In aerospace, it is a little bit mixed because the engine suppliers are so important to them, and they're separate companies like Rolls-Royce and General Electric. And in electronics, it turns out that the OEMs oftentimes have less market power than some of their suppliers, say Foxconn. That said, there was an important revolution when tiers were brought in. The idea was, and I'm going to use the aerospace industry as an example. At one point, Boeing would have something like literally, 1,500 suppliers. And they would actually design the components and they would give them to the suppliers and say, you all build the components according to this. And what happened is with the 787, which is a very clear example, they moved to a build to spec relationship. And in that case, what they did was they said, okay, here's some things you need to do. Here are our needs. We're not going to tell you how to build your component, but we're only going to tell you what the end product is. And in this, they explicitly said that they were following the automotive industry, which has done this beginning about 20 years earlier. And in their case, for example, I'll talk a little bit about automotive seats, which don't seem that complex. But it turns out there's almost 100 parts that go into seat systems. And those are designed by contractors like Lear, Johnson Controls. And what they do is they're the ones who actually do this build to print. And the idea is that they know seating subsystems better than, say, General Motors. And so the thought is that if we push this systems engineering, this integration down to the suppliers, that they will be able to get more out of them and their suppliers than, say, General Motors could. And for example, Lear has been able to reduce their product's weight by 30%. And it is thought that if the automotive OEMs had tried to do that weight reduction directly, they wouldn't have been able to do so. So let's go back to Boeing for a moment. So Boeing pushes all this integration capabilities to the various component suppliers. Now, the problem they found, because they were trying to create this revolution in the space of 7 or 8 years, is that some of the companies that they would push this integration to learned how to do it pretty quickly and did a great job. Others, not so much. In fact, it got to the point with Chance Vaught in South Carolina, which made the verticals, which are part of the tail, that Boeing had to re-insource that. So they actually went out and purchased the company and they paid $1 billion to do that because the systems engineering integration was not being done effectively at Chance Vaught. The other thing they found out is that doing this integration work, when you have 1,600 parts that are going to 1,600 suppliers, is a different animal from dealing with when you're building to spec among a dozen primes and maybe a couple dozen other major suppliers as well. And the reason for that is because all those suppliers, those tier 1 suppliers, are doing systems engineering. They have the issue that if their engineering actually impacts the other tier 1 suppliers. And so what happens is, because this isn't all held in Boeing anymore, Boeing figured out they had to create an organization that would actually track all these relationships between their suppliers and then mediate them and resolve conflicts. So those are the two major things that happened with the Boeing 787. And the 787 actually is seen as not a success. I actually think it was, in a sense, that it developed the capabilities that could lead to better airplanes in the future. Interestingly enough, when people talk about the 737 MAX, the 737 MAX actually kind of reverted back to the original organization in some sense, and that's part of the reason there were so many problems. I can go on with that if you're interested later during Q&A. Okay, so the tiers manage their sub-suppliers, and interestingly enough, the tiers actually manage their own sub-suppliers who actually are tiers themselves. So there's this whole pushing of the integration function down the line. And interestingly enough, that has led to a situation where the number of suppliers overall, for example, that will supply an airplane has actually been dropping over the past decade by a factor of about 5x, actually. Modularity is also another major trend. Now, modularity is the idea that you have a minimal number of interactions between two different components in a product, and they're very well defined and they're very well understood. So think of your USB connection in your computers. That is modularity at its finest. Now, the reasons for this are numerous. One is if there's a minimum number of interactions and they're well understood, then the overhead in terms of managing those interactions by the OEM is lower, and hence more tasks can be done in parallel and they can be done faster. And also you can have more direct suppliers, so it can flatten the structure because there's less burden from each supplier that needs to be managed by the OEM. It also minimizes re-engineering. And the reason for that is, since the interactions are well understood, if you have one component that turns out to be problematic, it isn't going to have the same number of knock-on effects as one that is more integral, less modular. It also enables innovation. It is thought, for example, in the personal computer industry, the reason there was such a blooming in the early 80s, and it's continued to this day, was the fact that IBM at one time made all the personal computers in-house, but they decided when they were going to go to a wide scale and bet their company to some extent on personal computers in general, what they did was they made it modular in the sense that all these components could be developed by separate firms. And then what IBM would do is bring them back together and create a coherent product. Interestingly enough, of course, once you get to that point, well, you know, all these components could be innovated separately. So for example, monitor technology, it's been getting better really fast. And that's okay, because what's going to happen is, as those monitors get better, it really doesn't impact the rest of the computer that much. There might have to be upgrade in the digital processing chips, but that's pretty much it. The other thing is it facilitates backup planning. Again, if you have a module, and you can take some risks, technically speaking, because if that fails, it's fairly easy to slide into a backup. And Dell has done this a number of times. I mentioned the USB connector as modularity. Now, what's happened is that some of those, USB is a great connection or great example, they've actually become standards. So they're not particular to one corporation. They're not particular to one product. They've become standard for the industry. And it's interesting to talk to these other industries. And when you talk to them, you don't really realize how many standards there are. It's almost like asking a fish in the ocean to describe water. They don't really realize it's there. But if you look at standards in the automotive, and even more so in the electronic industry, there are ISO standards, there are Society of Automotive Engineers standards, and so on. There are just so many standards. So for example, the communication in an automobile between the module that controls its engine and the module that controls its chassis and the module that controls its transmission and so on, these are not particular to any particular product or company. They are universal. And so it becomes actually easier to swap suppliers in that sense. And it also makes engineering a whole lot faster because these interfaces don't have to be designed. And it has all the other advantages that we talked about with modularity, only more so. And it's so important that where these standards don't exist, there's a whole lot of effort that is invested by these firms in creating standards. And oh, by the way, if those standards actually reflect what's best for a given OEM, so much the better. At a really extreme example, in the electronics industry, it used to be that there were books. Toshiba would have a book, a catalog. Texas Instruments would have a catalog. Hitachi would have a catalog. And literally, if you wanted a 7400 chip, 7400 is a type of chip, you could look into Hitachi, they'd have one. Toshiba would have one, and they'd all have the same name. And also Toshiba and Hitachi. And they'd all be the same, and they'd all have the same characteristics, and you could basically pick whichever one you wanted. You just open a catalog, and you're there. Everything about those was well understood and documented. Lastly, there are trends in the digitalization. A lot of this, honestly, is what we call blocking and tackling for all practical purposes. So I was talking about a week ago with an executive that ran the electronics controls, and in fact, all the electronics, it turns out, that have anything to do with a major truck OEM. And I asked him about, well, you know, do you have common tools up and down the supply chain? And he said, we mandate that. They're all going to be the same. Okay. And I kind of knew that, but from when I actually worked for Ford Motor Company, it was true there as well. When this has failed and there aren't common supply chain rules, it's been quite a mess. For example, the Airbus 380, this is from the early 2000s. They had a different CAD software that was used by their supplier in Germany for their fuselage, and also in France. There were two of them, and they basically made each about half of the body. Eventually what happened is all those body segments were brought together in Toulouse, and turned out they literally did not fit together. And it was because, when it was studied, turned out it was because they had different CAD systems. So, shared CAD, shared engineering, change orders, tracking, and so on. Project management tools as well. It's also possible, and there's some evidence that this might be going on at an integration level. For instance, Google is starting to do some of the same things in the healthcare industry, to have all the various suppliers of electronic health systems be able to speak to each other, speak to the government, and speak to institutions such as hospitals. There's also a trend towards deeper transparency. COVID has actually revealed the lack of transparency in OEMs being able to see in their supply chain. One study I read, this is only a month ago, that only rather 60% of companies had visibility. That is, they knew who their suppliers were 2 tiers into the supply chain or less. And this turned out to be a big problem during COVID, because what would happen is, almost, if you had a bolt supplier, bolt and nuts, in China that was closed down, it would eventually stop an assembly line in the United States. It would take a while to ripple through, but it would happen. There's another advantage to transparency that's come out recently, which is if you really know your supply chain, it enables you to do things more effectively with, for example, reducing your carbon footprint. It also would help with, for example, avoiding labor that is paid too little or is under abusive working conditions. Finally, there is telemetry that's going on with products. So what that means, for example, at that trunk company I was mentioning, but also a John Deere, which makes commercial tractors. What's been happening there is they're keeping track of things that are going wrong with their products that are in the field. And by products, I mean all their products that have been sold. What's gone wrong? What is going on with warranty? And then once those are brought in, if some of their products have had problems, then they can monitor what's going on with other products and determine whether those individual products, let's just use trucks, are going to have problems in the future or not. And also predict when those are going to happen and take according actions. The other thing is all that data can be fed into future designs. So with that, I am going to close out this presentation. This is the current state of the art. The trends in the future are building upon the things I've discussed, but there are a lot of interesting things that are going to happen in the future. And so with that, I would like to thank you, and we can move to the question-answer session.